let's go ahead and get started. I just reprinted this from before. This is the mass percent. One of the things you need to remember from last class's lesson is that the percentage of each element in the same compound will always be the same. That's something that is important to recognize. And so going into what is an empirical formula. How many people know the word empirical? What does it mean?
Empire.
What else could it mean?
Grand, major, basic.
I feel like there's something with math. There is something with math. And the empirical formula is actually the simplest formula. And what do we mean by that? And you may want to annotate as you're going along. And so when we say empirical formula, we're actually highlighting the simplest ratio of elements in a compound that can exist. So it's actually the simplest ratio of elements in a compound that keeps the mass percent. So in ionic compounds, all formulas are empirical formulas in ionic compounds. But in covalent compounds, that's not so. There can be multiple compounds that have the same ratio of elements in that compound. And so pretty much for covalent compounds, you're going to need to figure out the empirical formulas. Sometimes you'll be asked for ionic compounds, but if you know how to name the formulas, there's literally only one way to get the formula. All right, so make sure you're writing this down and the formal definitions on the next slide for both empirical and molecular formulas. And we'll write out some examples. Welcome back. Pausing. We are done writing. Sarah, you may want to take a quick picture. About 20 seconds before we move on. Okay, so the empirical formula. This gives our lowest whole number ratio, and you may want to underline or circle whole number. Meaning there will never be decimals in your final answer or fractions in your final answer. So no decimals, no fractions. No decimals, no fractions. You can only give whole numbers. And so this gives us the simplest ratio of atoms in a compound we can have. And so molecular formula may be different than the empirical formula because it's whatever the chemical formula for the actual compound we're studying is. And it tells us exactly how many atoms of each element we have in that compound. And so I wanted to give you this example. It's a common one. This is glucose. That is the specific type of sugar here. Glucose has the molecular formula C6H12O6. But that's not its empirical. What would be the simplest ratio here of carbons to hydrogens to oxygens? Can you figure it out? What would you do? Not CHO. Close. CH2O. And so the idea to go from the molecular formula to the empirical formula is you would divide by the largest number they have in common that has a mass term. That's called the greatest common factor. The largest number they have in common. And so what number could you divide 6, 12, and 6 by that would keep all of these whole numbers? 6. So you would divide 6 by 6, 12 by 6, 6 by 6. And that would give you the empirical formula, which is C1H2O1. And it turns out, if you were to do a further study in biology or further study in
Next
They're off
class.
by now. No, they're saying that it's 7:10 a.m. because it used to be. We're an hour early. So they're working on fixing it. Mr. Garcia said he put in the work order because it has to be, I think, fixed by the district. Can't fix it from the school location. Anyways, so this would be the simplest ratio of atoms in this compound. But all monosaccharides that are, all monosaccharides, which, how many of you know that what that means? Monosaccharide. It was something you learned in biology. One simple sugar, right? So all simple sugars actually keep this ratio. Not only glucose has this ratio, but fructose has this ratio. There are other, and galactose has this ratio. And so you can actually look, if you were to do a further study in biochemistry or biology or chemistry, you can look at this empirical formula and go through a class of compounds that has that empirical formula. And so you may wonder, well, how would I know which one I have? Like, is it glucose? Is it fructose? Is it whichever? Then you would need to employ other techniques in order to figure out, for example, what's the molar mass, and then there's other analytical techniques that we can look at to see exactly what we have. But that's the idea, is that you can derive from this, you're like, oh, I know that this is the class of compound that I have. This is a monosaccharide. Now, is this biology? No, so we don't really look into that here. We're just doing the math. But it does have relevance in a future study. All right, so let's say that you had C6H6. What would be, and that's why this is blank, you can fill this in. What would be, for this molecular formula, the empirical formula? Perfect. So molecular formula to empirical formula. This would be C1H1. Let's try another one. N1H3. What would be the empirical formula for N1H3? N1H3. The biggest number they have in common is 1. Divide both of them by 1. Do you really have to do that? No. So it said on the last slide, sometimes the empirical formula and the molecular formula will be the same as each other. Sometimes it won't. What about C4H8O2? What would that be? C2H4O1. So that's just the idea. You would find the largest number they have in common, you would divide by it, and that would give you the empirical formula. That's the simplest way to divide the number in common. So here it would be dividing both by 6. Here dividing by 1. And here dividing by 2. To get 2. So far so good? Here's the deal. The technique you're going to see is going to give us a way to get the empirical formula. And then after that, we're going to figure out a way to go from the empirical formula to the molecular formula for the specific compound that we have. I did want to bring up one more example while we're here. What about something like this? What would be the empirical formula here? What's the largest number in common? Did we write one? I did hear just like training wheels, but if you were to actually see a question, would the 1 be written? So what's the number for barium here? The empirical formula is the same. Something you may want to point out, this is an ionic compound. And by definition, ionic compounds already give the simplest ratio possible, if you may remember. Already gives the simplest ratio. You may remember when we were initially forming ionic compounds, let's say we had Mg plus 2 and O minus 2. We never said that was Mg2O2, did we? What did we say that this compound would end up being? MgO. So that's what I was saying earlier when I first brought it up. When you have an ionic compound, you are going to be given the empirical and the molecular formula. It's only for covalent compounds that they can be different, because covalent compounds can be much larger. All of your organic molecules, all of your biochemicals, like all the large molecules, are covalent, not ionic, just FYI. All right, so moving forward. This is just examples, and I printed this all out for you, of different compounds. Notice they are organic. That's going to be our final unit of study. It's carbon-based compounds. I mentioned this at the beginning of the year when I talked about the 5 branches of chemistry. There are 5 branches of chemistry. Just so you're aware, the current study we're in, like right now in this unit, is analytical. So if you actually like the math in this unit, then you like analytical chemistry. For the most part, that's the main thing that we're looking at in this unit of study. Whereas with organic chemistry, this is the study of carbon-based compounds. It's totally a different style of chemistry, and you'll see it in our final unit of study, because we'll go over it in end of April and beginning of May. That'll be the last one. The good news is that the way we do it in pre-ACE is we only go over basics, so it's important stuff, but it's not the most difficult unit of study. So I know that you're all kind of brain fried when we get to testing season, so I try to give something that's easier than what we're currently doing. And so that'll be our last unit of study. However, organic is carbon-based compounds. Notice that you have these 2 compounds have the same ratio of carbons and hydrogens, but they are different. Ethine, which we call it acetylene, is common name. This is a gas that's used in torches, so it's basically used as a fuel. And many organic compounds are used as fuels. Whereas if I have styrene, this is polystyrene. Styrene is used in making polystyrene, and these are what we use for packing pellets, if you've ever seen packing pellets in packaging. And it's also used, we use it in little foam cups. If you've ever had coffee in a little foam cup, that's polystyrene, CHH is its molecular formula, which CH would be its empirical formula. Now, how good is this for the environment? Terrible for the environment. Anybody want to take a gander at why?
It's not biodegradable.
It's not biodegradable. Oh wow, you all are fantastic. It's not biodegradable. It doesn't break down, and this is actually because it is completely non-polar. And non-polar, we're going to learn when we get to organic study more, means unreactive. I think I've mentioned it in passing, but non-polar molecules are not chemically reactive. They cannot be broken down by acid. They cannot be hydrolyzed, which means they're not biodegradable. And so you can burn them, but then they release toxic gases into the environment, so not great. Unless you make something alternative instead of what they're currently making. And that is an active area of research, making better biodegradable materials. All right, so that was just a brief introduction to the difference between empirical and molecular formulas. But as this whole unit is, it's all math, isn't it? So we're currently in a math unit, and what we have to do, yeah, every question is pretty much a math question in this unit. As I said, it's deeply into analytical study. If we were to talk about this is not polar, this is unreactive, it's not biodegradable, that's actually organic chemistry. So those discussions are in organic chemistry. What we gotta do is this. Steps to finding the empirical formula from the percent composition. So what your goal is to find out how many of each element is in A. That's the goal. When you're finding the empirical formula, you want to find out how much of each element you have in a compound. And there is a step-by-step manner to do this. These are the steps. In the past, what I would have done is printed out just this slide, given it as a handout, and then you have to write down all the questions instead of giving you the full guided notes. But I'm trying this year with giving you the full guided notes to see if that's helpful for you in terms of how you perform on the exams. like on the in-class exams. So, step 1, change the mass percent to grams. Meaning, whatever mass percent they give you, you literally just drop the percent and write G instead. And this is because mass percents are based off of 100. So you're saying 100% equals 100 grams of the compound. So the reason why we do step 1 the way we do is because you can relate the percentage to the amount of grams. Because it's mass percent, you can base the compound off of 100 grams. And then the next step, once you've done that, is to take the grams of each element from step 1. Grams is a mass, right? Does mass tell you amount of objects? If I say I put X number of objects on a scale and it tells me a mass of those objects, can I figure out how many objects just from the mass? Not really, right? So if I'm looking at these crayons and I just put it on a scale and it says mass is 500 grams, that's not enough information.
Good.
What else would I need to know?
I need to know the mass of one crayon.
I would need to know the mass of each crayon, right? In order to figure out the amount of crayons. And so the idea is that you are going from mass to amount. And in the periodic table, our link for that is the molar mass or the atomic mass. So when they say convert grams to moles, that means we're going to be using the atomic mass to do that. And why I said the grams to moles calculation we learned back in the first part of the unit was the most important one. That was the most important link we were going to do. And then so after we've got the moles, remember moles is an amount. It is an amount. The problem is the moles you're going to get usually are a decimal or a fraction. And so in order to change it out of a decimal or a fraction, the next step is to divide by the smallest number. And so that's what you would want to underline. And we'll, of course, work through this with practice questions. Don't worry. And then finally, step 4 is only sometimes. So this is not always needed to be done. Steps 1 through 3 are always needed to be done. Step 4 is sometimes. If you end up with, after dividing by the smallest number, you still have a decimal or a fraction, it's here. You're going to multiply to get a whole number. And so we're going to, I used to write this on the board, but I was last night, I was like, you know what, I'm just going to give it to you all. So common multipliers for step 4, we'll go back to this. Some of you might be like, yeah, miss, I know that. If your decimal ending is 0.25, in order to get that to a whole number, you would multiply by 4. Because, like, that's close to 0.33 is like 1/3. So in order to get everything to a whole number, you would multiply by 0.5 is the same thing as 1/2. So that's why you multiply everything by 2 to get to a whole number. 0.67 is the same thing as approximately 2/3. And then 0.75 is the same thing or very close to 4 if you round to that. So that's something important to note. We'll come back here as needed. But let's go ahead and take a look at the first question. Compound is analyzed, probably in a mass spectrometer, and found to contain specifically 25.9%, and these percentages are by mass. So to be clear, you're only looking at mass percentages here. 25.9% of all the mass of this compound is nitrogen, and 74.1% of all the mass of this compound is oxygen. And you are asked to figure out what is the empirical formula. We're going to work through the steps and see if we can figure this out. What's step 1? You got it. It says change percent to grams, right? Change percent to grams. What does that actually mean?
25 grams.
Right. So you say I have 25.9 grams nitrogen when I have 74.1 grams of oxygen. And together that would add up to 100 grams of the compound. So for every 100 grams of the compound I have, I know 25.9 of those grams are going to be nitrogen, and 74.1 of those grams are going to be oxygen. Because these are mass percentages, that's why you could just directly relate it. That's step one. What's step two? It's gonna be the part that you all whine about the most, baby. Step two is change grams to moles, right? Rachel? Yes. Grams to moles, what was that? Wasn't that dimensional
High-dimensional
analysis? So this would be these would be my givens. So I have two questions to solve. I have to do 25.9 grams of nitrogen. How do I change that to moles?
You get some molar.
What a one in the middle.
Put a 1. And how am I going to change that to moles?
You multiply it by the molar mass and then with 1 mole.
We go back to this, right? 1 mole is the number of grams. You are going to have to memorize this. This is the relationship you've got to memorize. I'm going to take this off on the day of the test, but I have it up here as we're learning. 1 mole equals number of grams, which is the molar mass or the atomic mass of that element, right? So what's the atomic mass of nitrogen?
It's 14.
So we do 14 grams of nitrogen on the bottom. Why
So they
14 on the
cancel.
bottom?
Because
We have
that's the
grams.
molar mass.
And then the one on top.
And the 1 mole on the top. And so this cancels.
And then
And we're literally just, and see if you can connect with this. If I put a number on the bottom, it literally means I'm just doing a division. So it's just 25.9 divided by 14, which is, so I know that I have 1.85 moles of nitrogen. Now, for those of you that got this, you understand how to go from grams to moles, and you understand that it's division. You could just remember divide by the molar or the atomic mass, right? Divide by the atomic mass, which for an element is the same as the molar mass. And I believe I did put that in here. Or I said you was on it. I changed it a little bit just so you could have the proof of why this happens the way it does. But you could just remember divide by the atomic mass. Well, that's nitrogen. Don't I have to do this again for?
Yeah.
Oxygen?
Yep.
So now it's 74.1 grams of oxygen over 1. And then what goes on the bottom, what goes on the top? What's the relationship between oxygens, grams, and moles?
1 mole goes to the top.
The atomic mass will go on the
16
bottom.
G goes.
Right. So 1 mole of oxygen is 16 grams of oxygen. And I know I, again, have to divide these two numbers. 74.1 divided by 16. And that gives me 4.63. Before you ask it, if you haven't yet, in terms of rounding, I would keep at least 3 significant figures through the process, regardless of what the percentage they give you is. Keep at least 3 significant figures throughout the process until the end, because it's very easy to make rounding errors here because of these decimal endings. So this is just a guide. For empirical formulas, I do advise, I'll put your question in a second, keep 3, and you could keep more than that. Keep 3 or more sig figs until end. You round at the end. Yes.
And then you get
25.9 divided by 14. I got 1.85. Did you divide 25 or did you divide 25.9? Because I think I heard you say 25 earlier.
Yeah.
It's 25.9. All right. So we're at the end of step 2. Step, yes. When she gets back, you can move next. Divide now. So here's the idea. Once you have moles, remember moles are amounts. They're a grouping of an amount of atoms. So literally, because this is moles, you could put this in a chemical formula. So in step 3, and I'm just outlining the steps in the first one, which is divide by the smallest number, I do want to give you the reason why. Right now, you have N 1.85 and O 4.63. So what you're communicating is that when you have 1.85 moles of nitrogen atoms, you have 4.63 moles of oxygen atoms. Well, first of all, does it make sense to say you have 1.85 nitrogens?
No.
In any world, does that make any kind of sense?
No.
Would you ever communicate that to anyone? No. And so that's why, in order to figure out, oh, well, what's the simplest ratio between these two? Because that's the empirical formula, right? You would divide by the number they have in the smallest number. And so it would be 1.85 is the smallest number. So you basically look smallest number, so you divide by that. And that gives us N1 and O what? 4.63 divided by 1.85 is 2.5027, Now, here's where you're going to have to make a decision. First of all, is that close to a whole number?
Yeah. Around the side.
It's not close. It's actually midway. It's not close. And I'm going to give you the guidance for that in a moment. Is that close to one of these numbers?
Yeah.
For step 4. It's really close to this, isn't it? So this means we are going to have to incorporate step 4, which means that if you find out that you get something that has an ending that's fractional, you have to find a number to multiply them both by, and this is what step 4 says, multiply to get a whole number. And so what would you have to multiply 2.5 and 1 by to get a whole number? The simplest whole number ratio, by 2. So you do it for both. And your final answer, and this is step 4.
So if it's not perfect, so it's 5.005405.
So that brings up a really good point. How do I know what's good enough to round? Like, what is the standard? What do scientists use to say that this is good enough to round this to the nearest whole number? And I'm going to write it on the other slide after you all write this down. I'm going to give you a moment first. N205 is the answer. How do I know that I can round 5.005 to 5? That's the question. All right, I'm going to go back here. I just want to address what decimal ending is close enough to round to the nearest whole number. So what do scientists accept? It's plus or minus 0.08 from experimental data. Meaning, if you had gotten here we had 5.005. This is definitely within 0.08 of 5. That's good to just cut to 5. If we had gotten 5.10, would that be close enough to round to 5? No, and we would technically make it multiply by 10, because that would be 0.1. That would be multiplied by 10. Is 4. So this is good to round. This is not good to round. Is 4.97 close enough to 5 to round it to 5? Like when you do all the work, is 4.97 close enough? Yeah. So in our question, as long as it was between 4.92 and 5.08, that would be close enough to round. That is the bar that we use, and you'll need to know that for the homework that you have today. Because especially in the digital homework, there's some that if you don't round right earlier, you'll be off of where you're supposed to be, which is why I said when you're doing this, make sure you keep 3 or more significant figures until the end. And some of you do this like I do and just keep your answers in the calculator as you go along, and that ensures that you keep the right amount of significant figures. Don't round too much is what I'm telling you. All right, so if you need any more time here, I'm giving a little bit of time for you to take a picture if you need it, or finish writing down, and then we are going to go ahead and move forward. So this is a little bit more of an involved process than finding the mass percent. As you could see, mass percent was less steps. This is more steps. Welcome back, Damien. And I guess that's the bad news. The good news is they are the same steps every time. And if you are going to take the AICE class, it's the same steps there too. Like it's no different. You're learning the strategy here. Ready for the second one? Finally, empirical formula, given the following information. This time, I'll pause for a couple of minutes. If you felt from the first example that you are pretty confident, you can look at the steps and try it yourself. Please do. And then if you're like, nope, I will wait for you, Ms. Lee. I will start in a couple of minutes. I just want to give that heads up to try this one yourself first. This one doesn't say your turn, so I'm not going to check it. The next one after that does. Change grams to moles. So you got to do it 3 times. Right? One of them is pretty easy to know if you know it's molar mass. A couple of minutes in advance to work, and then we're going to go ahead and finish. All right, so here we go. Step 1, I would say 40 grams carbon, 6.7 grams hydrogen, and 53.3 grams oxygen. That's the mass relationship for these elements in this specific group. Step 2 is the most involved because you have to change the grams to moles, which means you're technically doing grams to moles 3 times. And so step 2, I'll set each of them up properly, is 40 grams carbon over 1. You got to cancel out the grams. How do you know what number goes on the bottom here?
Atomic mass.
Whatever the atomic mass is always going to go on the bottom because grams always have to cancel. You're always dividing by the atomic mass. So 12 grams carbon, 1 mole carbon.
And so
Our first answer. 40 divided by 12 is 3.33 moles of carbon. That's 1. But we got to do this a total of how many times? 3. So now we do the 6.7 grams of, I'm just going to use my space here. Hydrogen over 1. What?
You get 3.3.
Yeah.
Now,
1.
6.7 grams hydrogen. How many grams of hydrogen are there in a mole of hydrogen? I remember when I was learning this as a student myself, I was like, oh, really? This never said they're this big. It's like 1 gram hydrogen is 1 mole of hydrogen. It should be 6.7 moles of hydrogen. And that's the second one. And what's the third one?
Oxygen.
3 grams oxygen.
1.
And you're dividing by
16.
16. And I'm only writing it out to prove like this is what it is, but you are allowed to just simply take your given amount and divide by the atomic mass. As long as you understand why you're doing it. So 53.3 divided by 16 is, again, 3.3. Sorry. So now what? So what's step 3? Step 3, we can now, because we have a mass, we can put this in our formula. So C is 3.33, H is 6.7, oxygen is 3.33. What do we divide by?
3.3.
The smallest number, right? If two of them are the same, they're both the smallest number in this case. You divide them all by 3.33. That automatically tells you that, carbon and oxygen are going to be 1, because anytime you divide by the same thing, that's the whole point, is to try to get them to whole numbers. And so we get C1, H, 6.7 divided by 3.3, which is 2.01. And then oxygen 1, and you have to make a decision. Is 2.01 close enough to 2 to just cut it here and be like, I don't need a step 4? Or do you need to multiply by 99? This is round. This is going to be a carbohydrate. Nobody would buy this. What? By 100? By, we multiply by 100, yeah. To get C 100, H 201, O 100, but that wouldn't actually be different. Like, it would be this. Because this is experimental data, so there is a time to round. Because all of this is actually coming, like in real life, IRL. You would put a sample in a machine. The machine would give you this percentages or something close, and then you would figure out what is most likely what my sample is. And this is the procedure to do that. So far, so good?
Yeah.
All right. Now it is your turn. So, go ahead and try this one yourself. You've got 5 minutes. Once you have the answer, raise your hand, and if you have it right, I'll stamp it. I'm going to go ahead and work it out myself as well. You're the first class. We're back on B day being first, so you're the first class. So I'm going to go ahead and solve it. Yes. Sure, go ahead and grab one here while I'm working this out. So once you have it, raise your hand. I have the answer. Oh. You've got 5 minutes, like I said. If you have it beforehand, raise your hand, and I'll check it. I will go ahead and solve it afterwards so everybody gets it, but I want you to try it yourself first. Raise your hand once you have it so I can. Yeah, go ahead. Anybody else, as you're ready, raise your hand, let me know, and I'll check it. Got about 3 more minutes still. At 8:47 on the right, remember, once you have the answer, raise your hand and I'll check it. You should be working on the questions. Yes. So we have to divide them all by the smallest number. So yeah, so we'll all get divided by this number. Oxygen will automatically become figure out what the other two are. Right. In 1 minute, I'm going to start going over the answer if you didn't get it right. Remember to collect my stamp at the end of class if you didn't get it during the 5 minutes. Okay, let's go over it. So I'm going to go a little bit quicker through the process this time. This is just double checking that you got it. For step 1, we know that we have 62.07 grams carbon. We have 10.34 grams hydrogen, and we have 27.58 grams oxygen. If I want to write less and still get full credit, what can I do? Just divide by each of these atomic masses. So we would divide this by, we know it's 12 grams in a mole. This would be 1 gram in a mole for hydrogen. And for oxygen, it would be 16 grams. So we divide by each atomic mass. And that gives us for carbon. My rule of thumb is to write 3 numbers. So 5.17 moles of carbon. This stays 10.34 and 1.72. Students often ask me, so I'm going based off of questions that I've been asked in the past. Yes. What's enough for Cambridge? Like in terms of method marks, this is enough. As long as you show clearly that you divided by each element's atomic mass, and then you divide by the smallest number, that's enough work for them. You don't have to show the whole dimensional analysis process. The reason I showed it in the first 2 questions was so that you understand why you're dividing by atomic mass, not multiplying. So make sure you get your steps right. It's always dividing. Divide, divide, divide here. Until if you needed step 4, but you don't here. So you divide each of these by the smallest number. When you analyze these 3 numbers, what's the smallest number? 1.7? 2. Divide each of these by 1.72, and you get really close. We know this is going to be close to 3. This is 6. And this is 1. And so your final chemical formula would be C3H6O1. Good job to all of those of you that got it. Let me stamp yours. For those of you who didn't get it, make sure you're writing this down in the next minute or so we can move on if you didn't get it on your own. Or it took longer than what I had done. So you're going to attach this to your notes? Okay. Yes. You got it now? Do you know what happened? Like what the mistake was? Ah, okay. we have one more topic to cover. We have now spent time going through the process of determining the empirical formula. We know how to figure out the simplest ratio. But this lesson is about empirical formulas and molecular formulas. So how do we go from the empirical formula to the molecular formula? I showed you at the beginning of class how to go from the molecular to the empirical. So basically, how do we go backwards? When given the empirical formula, how do I know which version of this molecule do I have? And that's going to be the last topic. I have it printed for you, so we're going to move ahead in the notes to the last thing. How does the molecular formula of a compound compare with the empirical formula? And you're going to see a chart here. Do not memorize. But you need to understand the comparison. CH, and you may want to write this down. CH is not a molecule. There is no molecule CH that naturally exists on our planet. Why not?
Because it's compound. It's
Check this out.
it's so unused.
Right.
Yeah.
This is not going to be a thing. It's not going to be a thing. This hydrogen cannot take any more electrons. This carbon will never meet its octet rule. This is unstable. Totally unstable. So this empirical formula does not represent an actual molecule that exists. However, the molecules that exist with that empirical formula, they obviously do exist. And so at Fine, just to map it out, we've drawn this before, back a while ago. It would be like, bless you. It would be like this. And what would Fine look like? Right? But it is something that actually exists. So the molecular formula is always going to be a molecule that exists, whereas the empirical formula may or may not be something that actually exists, but just gives you that simplest ratio of carbons to hydrogens in the molecule. So how do I go from the empirical formula to the molecular formula? You're going to have to be given one additional piece of information in order to get it. And that's really just what is the molar mass. Because if you can figure out the molar mass of the empirical formula and the molar mass of the molecular formula, the idea is that the molecular formula would always be some kind of multiple of the empirical formula. So the molecular formula, and you're going to want to write this down in your little bit of space, molecular formula is always a multiple of the empirical formula. Now, could that multiple be 1, like NH3? It could be. But it's some kind of whole number multiple. Welcome back. So you're going to want to write that down before we get to the math we have to do with it. I'm not drawing out all of these. But I just wanted to use this as an example, that the empirical formula is not always something that exists. And so then we're going to develop a method to figure out. Go ahead. The molecular formula given the empirical formula. See, pretty much almost everything's done right. So just a second heads up on moving forward. All I wanted to bring up here is that the molecular formula is a multiple of your empirical formula. We're going to use that information to help us solve questions. Here we go. Finding the molecular formula from the empirical formula. So typically what happens if they're asking you for the molecular formula. So go ahead and annotate the question. The empirical. Typically what you're going to have to do, or what you're given, is the molar mass of the molecule. So this is the molecular formula's molar mass. And you're given another piece of information. And this piece of information has to be given to you to solve. You're given the empirical formula. So how could I figure out from the molar mass of the molecular formula and the empirical formula what is the actual molecular information is missing that you could easily get. That could give you the difference in the mass of the molecular formula and the mass. Right. So step one in developing our strategy. Step one should always be to get the molar mass of the empirical formula. And let's figure out what that is now. So CH4N. How much work do you have to show in getting molar mass? You just have to show what you added and what you multiplied. So how would we get the molar mass of CH4N? What does that look like? What's the mass of carbon? So 12. What's the mass of hydrogen? 1 times 4, right? So 4. Are we good with understanding that? What's the molar mass of nitrogen? Add that all together. You should get 30 grams per mole. So, now here's where you gotta think. My empirical formula has a molar mass of 30 grams per mole. The information they've given me is the molecular formula's molar mass is 120 grams per mole. The relationship between the two is that the molecular formula always has to be some multiple of the empirical formula. So how can we figure out what that multiple is? But the other way around, because we want a whole number, right? So you would divide. So step 2 in developing the strategy. Step 2 is to divide the molar mass of the molecule by molar mass of the empirical formula. So what does that actually look like? 120 gram per mole divided by 30 gram per mole. These units cancel, and you just get a number. What's 120 divided by 30? We call this a multiplier. Because what this indicates is that our molecule is 4 times as large as the empirical formula. So if we take the mass of the molecule and divide by the mass of the empirical, we'll always get some whole number multiplier. So we multiply everything in this empirical formula by 4. So that would be technically step 3, right? Step 3, multiply subscripts of empirical. And so what would that be then? If it's CH4N, what am I multiplying by? There's an invisible what for carbon? So we multiply each of these by, and your final answer would be C4, H16, and 4. So the actual molecule is C4, H16, and 4. The mass percentages would be the same because they have the same ratio. Yes. Yes, there's only one more question. This is going to be yours to try. So you've got a second, your turn. This is the last question. Waiting to see if everybody's done writing this example. I still see writing, so I'm going to wait. When you're ready, move to the last question. Again, I'm going to give you 5 minutes to try it yourself. You're getting a stamp from me if you got it correct. So the last question is the same as this one. Same type of question as this one, but I want you to try this method yourself. You got it? Say it out loud. Got it? All right, so try this last one. Raise your hand once you've got it, and if you need me to check your other one from earlier, please have me check that as well. And then we're going to talk, because this is the last slide, we're going to talk about your classwork and your homework, because you actually have 2 assignments on today's lesson, because this is best learned with practice. Remember, as you get the answer, raise your hand. I am going to start passing out the assignment for today. You have enough time that you could finish the written assignment before the end of class. So I want you to try to do that. There's also a digital assignment that's posting. If it hasn't posted already, it's posting very shortly, auto posting. And that digital assignment is due by the next class. I do want to give you a heads up once again on that digital assignment. If you do not round to if you round too much, you will end up with the wrong answer. So make sure you're keeping at least 3 significant figures for the digital assignment. Remember to raise your hand as you get the answer, and I will be stamping off on it for your credit for your notes. Very nice. All right, I'm going to also start passing out the assignment. You should try to finish the written assignment within class. It's only 4 questions, and based on the pace many of you have been working at, I believe you could finish this before leaving the class today. That way you don't have to do it.
Me in the background too. You want me to plug it in again?
Once again, there are 2 assignments. Get the written one done before the end of class if you can, and then the digital one you can do at home. This is the assignment. Did I give you the assignment? And I stamped yours already? And I stamped yours already, everything? I stamped both of yours already. This is the assignment. Try to do the written assignment now before you go. You're working on it? There's only 4 questions in the written assignment, so you can try this before you go. Make sure that before you leave that you're checking, that you're having to check your verbs. For the written assignment, you can work together, but you do need to work on the assignment. You just have to multiply all these numbers to get the final answer. This is the assignment. Let me check here. Very nice. This is the assignment. Oh, all right, very good. The assignment.
Isn't the multiplier 3?
Where did the answer that I gave you? You need to work it out as a little bit. All right, so you have about 20 minutes in class, so you can work together. There's 4 questions I would like you to get done before the end of class. And then the other assignment that's going to be the digital one, you can do that as homework so you get some extra practice. How do you do the homework? I do. I probably have to buy more tools because a lot of nail adhesives. That's bad. And this is one of the only classrooms that we have here. Got lots. I do. Whenever you get hurt. They're not like the big Band-Aids though, they're just like regular Band-Aids. So hopefully it's not too big of an injury. 3. You could write 3.225. You can write more than 3, but keep at least 3.
The problem is when you only do 1 or 2 significant figures, when you round, you might get farther away from like the whole number and think you have to multiply by something when you don't. That's what happens.
Yes. Now, are you ready for me to check?
All right, let me hit stop on recording.